Thanks everyone for joining our virtual fireside chat. We're really excited to be talking about lessons learned from AES deployment of dynamic line ratings. We're going to be talking a little bit about the collaboration between LineVision and AES, and get into some Q&A at the end. And so speaking today, myself, Karthik Rao, I'm VP of Client Success at LineVision. My team is responsible for implementing our transmission line monitoring technology with electric utilities around the world, and really making sure that they're achieving the outcomes and goals that they're hoping to achieve. And I've had the pleasure of getting to know AJ Hall from AES, and we've worked together now for well over a year. And really excited to have him joining me today for this webinar. So AJ, would you like to introduce yourself?
Sure. It's been, I think, almost 2 years,
Yes, 2 years.
Karthik.
Yeah,
So let's not
great.
shortchange it here.
I'm
So
glad.
AJ Hall with AES. I'm a portfolio management director for AES's Center of Excellence for Innovation, which is called AES Next. So we look at what technologies are going to be valuable in the future of energy that we're trying to accelerate at AES. And specifically, I work hand in hand with our utilities businesses in the US, as well as our renewables businesses in how do we bring more clean energy online, and we see dynamic line ratings as a key solution for that.
Great. So just a little bit of an overview of what to expect today. We're going to start off by kind of setting the stage on the utility landscape right now and the surges in energy demand that utilities are facing alongside the challenges around modernizing our grid. And then we'll get into the specifics around the project that LineVision has been doing with AES, both the motivations for the project, as well as what we deployed and what the results have been since we started getting the data. And then at the end, we'll answer any questions folks have. For anyone listening in today, we really do encourage you to submit any questions that you have. If you click at the bottom of your screen, you'll see a little button that says Q&A. Feel free to type in a question as it comes to you. You don't have to wait until the end to ask your question. You can submit your question at any point. We'll be collecting those, and then when we get to the end, we'll do our best to answer as many of those questions as we can. So with that, let's get into a little bit of the utility landscape and what we're seeing with electricity demand. For those of you who've been in the energy space for some time, you know that for a number of decades, energy demand was largely flat, but that has all changed just in these last few years. We now see that power demand is forecast to increase at 6 times the pace of the past 20 years. And so the question arises, why is that happening? And it turns out that there are a number of different trends that are kind of taking place simultaneously that are converging to drive that really dramatic demand in electricity. First and foremost is AI. We hear about this in the news all the time, this substantial amount of electricity required to run these AI algorithms in the data centers that power them. And so we're seeing data centers pop up all around the country and in different pockets around the world that are really just sucking up a ton of electricity and kind of pushing utilities to the limit in terms of being able to provide the sufficient electricity for hyperscalers and other big tech companies, as well as more upstart, smaller companies that are competing in that space. But that's all happening alongside the resurgence of manufacturing, particularly here in the United States. We're seeing a significant increase in industrial load growth as manufacturing plants and other industrial facilities start to pop back up and really start to consume a lot more electricity than they have in the past. And then, of course, there's the energy transition itself as we bring in a lot more renewable electricity and domestic power and try to electrify our economy. You see a lot of sources of energy consumption like gas-powered cars that are now switching over to electric vehicles, home appliances that are being electrified. These are all categories that are essentially net new sources of electricity demand that are, again, contributing to that 6x pace that we're seeing. And so the question becomes, how do utilities keep pace with this dramatic load growth? And there's a lot of different components to that, but one of the most important is the transmission system. Transmission, obviously, is essentially the backbone of our energy system and is critical to bring electrons from where they're being generated which increasingly with renewable power is often in remote areas, um, over to the population centers where the demand is highest and where the electrons are being consumed. And unfortunately, building new transmission is a really expensive and time-consuming process. It can take 10 or more years to build a new line, and that's largely due to siting and permitting issues that get in the way. And so while we're absolutely going to need to build that new transmission as well as reconduct our existing lines, um, utilities are increasingly looking for other tools in the tool belt to try to bring that capacity to bear in a faster and more cost-effective way. And that's really where LineVision comes in, to be able to provide a technology layer that allows us to bring that capacity to the grid in a much more flexible way, because ultimately we know that utilities are going to reap the benefit if they can bring on those new customers into their service territory and meet the demand from that load growth. So
Karthik,
how
if
do
I
we
can
do? Please, yeah,
jump
go
in
ahead.
here real quick on that slide. I just want to say, like, these challenges here are real to AES. So I'll get into AES's utilities in the Midwest in Ohio and Indiana, but we are seeing all four of these things in our service territories. And Karthik's point about it, this is really a how do we better serve our customers? Our customers are wanting, these large industrial customers, even customers that are buying electric vehicles, they want to be able to connect to the grid quickly and realize these benefits. However, it is very difficult to build out a grid to serve these growing needs quickly. And so that's why we're looking for new tools in our toolbox for transmission and to deploy to meet this growing challenge. So I just want to comment that these are real challenges we're facing, and we're going through it with our integrated resource plans and in Indiana and our grid modernization filings in Ohio. All of these things are top of mind and key drivers to enabling our customers and economic growth in our service territories.
Yeah, thanks for that, AJ. Really good insight and so helpful to hear that directly from you all, and something that we hear consistently from our utility partners that we work with around the country and around the globe. So let's get into a little bit about how LineVision thinks about these problems. So, first and foremost, when we think about why LineVision exists, it really was born out of a recognition that 99.9% of the transmission system is unmonitored. So what we mean by that is these assets are hung up in the air and they're conducting electricity and really powering our entire economy. But there's very little feedback on how these assets are operating in terms of, sensor data that can provide us visibility into how to best optimize those assets or how best to manage them or maintain them. And so we really see an opportunity to change that. And we do that by a combination of sensors out in the field, as well as software and analytics that we've kind of developed. Importantly, the sensors that we install are non-contact sensors, which means that we install the sensors on the tower, and nothing goes on the conductor itself, which means that no live line work is required to install this technology, no outages are required. And so it's a really safe and efficient way to deploy these sensors, and we can really deploy a large number of them at scale in a short amount of time. Our flagship product, and the one we'll talk about most today, is dynamic line rating. So what is dynamic line rating? Every transmission line has what's known as a rating, which is the maximum amount of current you can safely run through that conductor. And traditionally, we've used what's known as static line ratings. Static line ratings are calculated using conservative assumptions. So think about the worst case scenario. Let's say it's a really hot day, the wind isn't blowing, the line is already starting to overheat. Under those conditions, what's the maximum amount of current you can run through that line before you exceed the maximum operating temperature of that conductor? And whatever that number is becomes the fixed rating all year round. And so, of course, it turns out that most of the time we're not operating under those worst case scenario conditions. And so we're essentially leaving capacity on the table. So what we can do is by bringing in real world, real time data on the ambient weather conditions and the way the line is being operated, we can provide the operator with real time understanding on what the true carrying capacity is of that line. And by doing that, we move from a static line rating to a dynamic line rating, and we can increase the capacity of that line by up to 40% or more. And so we'll get into a little bit more of how we do that and how that's been applied to AES in a moment. But interestingly, once we deploy this technology, there's added benefits as well. So as you start to understand the position of the conductor in time and space, we're able to provide operators with information to be able to improve the asset management and reliability by providing them with situational awareness. For example, when the conductor might be at risk of coming into contact with nearby vegetation, if there's risk of icing building up on the line. Unfortunately, wildfires are increasingly a top of mind concern for utilities around the world. And so being able to know when wildfire risk might be of particular concern for a transmission asset, these are the kinds of insights that we can start to get from the data. And then finally, enhancing the reliability and safety of the grid itself by understanding things like asset health, right? For particularly for lines that may have been out in the field for decades or approaching, in some cases, up to 100 years. What is the actual health of that asset? Is it operating the way it was originally designed to? How do you bring a more data-driven approach to preventative maintenance, things of that nature? And so really see this as kind of a unified platform to really turn transmission lines into smarter assets. So with that, we wanted to talk a little bit about the project we did with AES, deploying some of this technology. So AJ, I'll hand it back over to you to kind of tell us a little bit about your company.
Sure. Thanks, Karthik. Yeah, to get into the weeds of the project with AES and LineVision, AES overall is a global company, operate in 12 countries. We have 6 utility companies. 2 of those are in the U.S., in the Midwest here in Indianapolis, where I'm based, and also Ohio. And you kind of see the diversity of service territory. We have very urban service territory in Indiana that's centered around Indianapolis. And then in Ohio, we have kind of the southwestern part of the state. And so really a great opportunity to deploy dynamic line ratings across a diverse set of assets. If you want to move to the next slide, Karthik. All right, so why did AES look into dynamic line ratings and look at the LineVision solution? Really goes back to the slide we had earlier on the challenges, right? We're seeing customer growth needs, we're seeing reliability needs, and so the need to have better monitoring on critical assets is something AES is pursuing across the board and not just on our transmission system. So first, we wanted to prove what's the cost-benefit ratio, right? What is the cost and what is the time to deploy this technology, and then what are the benefits for AES and our customers? And then some of those benefit streams are one around what's the capacity gains from DLR, but as we'll talk about in some further slides here, it's not just about percent capacity gains over static or ambient adjusted ratings. It's really about the better visibility into how these critical assets operate and allowing you to safely and reliably operate lines, as well as smartly plan the grid with data that you didn't have, grid planners and grid operators don't have without deploying dynamic line ratings. So you can see kind of an overview of the project, 100 kilometers of line or 62 miles for those of us stuck in the English system of measurement, and 42 LineVision Lux sensors installed across 5 lines ranging from 345 kV all the way to 69 kV, so kind of the sub-transmission level.
Yeah, and AJ,
next slide.
I wonder if, just before we move on from that, I think a lot of utilities that are maybe contemplating dynamic line rating, part of the challenge they have is just kind of knowing where to begin and knowing where they might deploy sensors on one line versus another. Maybe you could talk us a little bit of the process you guys went through to kind of select the lines for this project, because I think you had a pretty thoughtful approach to that.
Oh yeah, no, thanks for the question. Yes, I think almost 2 years ago today, LineVision and AES met in person in our facility in Ohio, and we kind of had a great brainstorming meeting, similar to the approach of this presentation, what is the capabilities of LineVision's technology? And then what are the needs of AES and our customers? And that led us to select about 15 lines or so across transmission lines across our service territories in Ohio and Indiana. And based on those 15 lines, and those lines were identified through lines that require more capacity because we're seeing more customer interconnections, lines that were concerned about their reliable operation, and lines that we frankly wanted to know more about from just because of their critical connections to local generation sources. And then LineVision performed line profiling studies, essentially looking at the geography of the line, the heading changes, the historical wind speeds, and all of those factors go into an estimated performance of DLR on these lines. So what is potential capacity increases that we could see, take into account there are other limiting elements than the transmission line. For instance, in a substation, you might have a wave trap or a relay that also might need to be upgraded if you want to achieve a higher rating. From these line profiling studies, AES was then able to select the 5 lines that we deployed the DLR technology on. So yeah, it was a kind of an iterative process, and LineVision really kind of helped us guide us along the way, but really involved, from a utility standpoint, a lot of different stakeholders, from operations, transmission planning, and then also our customer growth teams. So yeah, no, great question.
Super helpful. Let's get into some of the results.
Yeah. Okay, so we've had LineVision sensors deployed over a year now on our lines, and we have some very positive results here. So you can see 2 of the lines we're showcasing kind of at each end of the voltage spectrum. We've got a 345 kV line in Indiana on the left, and you can see the average capacity gain above static ratings was 43%. So a lot of bandwidth or headroom to be gained here by deploying DLR. And then compared to the cost of reconductoring that line to achieve that 43% gain, its DLR is only less than 8% of the cost of a standard reconductor. And most of the time, it's even above ambient adjusted ratings. And we'll get into more details there. And then on our 69 kV line, we were able to identify, and we'll get into kind of the details here, but the ability to increase this line through a targeted reconductoring solution that can achieve a $1.2 million in cost savings and avoid a year of construction time versus a standard reconductoring process. So overall, deploying DLR, the insights it provided and the additional capacity gains clearly proved out the cost-benefit ratio for us. And with these results, we'll kind of get into some other use cases beyond capacity gains. Karthik, do you have any questions on this slide for me?
No, I think we'll get into some of the specifics on where these benefits are coming from. But obviously, top line here, really impressive results, and been really excited to see what we've been able to deliver in this kind of first year of data collection.
Yeah, we can go to the next one. All right, so to zoom in a little bit on the 345 kV line. So on the top of the slide here, you can see a heat map that kind of shows what are the capacity gains based on the average capacity achieved for each hour of the day for all 12 months of our deployment. And so you can see in the winter months, like December and January, on the ends of that chart, there's a lot of capacity that can be gained. In fact, there's times when the line could carry double the capacity or double the electrons that our static line rating limited to. But then in the summer months, you can see that DLR, while still achieving 18 to 20% above static, there is less capacity due to the increased heat of the conductor and at times lower wind speeds. And so how do we compare this to a traditional transmission solution where we need to increase capacity? We looked at the lowest cost solution to increase transmission capacity is to string new wires on your existing towers. So hang some heavier conductor or bigger conductor on your existing towers, assuming that they can hold it. really DLR, this is where you get to DLR is less than 8% of the cost. It's roughly 45,000 per mile when you take into account installing DLR and then a 20-year software cost for the life of that asset, and then versus reconductoring, which is almost 600,000 per mile based on MISO or mid-continent system operator cost estimation tables. And really importantly here, the time to be operational. This is something we're hearing from our customers. How fast can you deliver this capacity? Reconductoring is at least 2 years in a very positive scenario, whereas DLR, we took a measured approach where it was deployed. We got DLR deployed the sensors in a month, but we wanted to collect 6 months of data before using it in operation. So that's why you see the 9-month timeline there. And then on the outage required, Karthik made this point earlier, these sensors hang roughly about 10 to 20 feet above ground, but well below the minimum approach distance of the live conductors. So our technicians were able to install these sensors without an outage, versus from a reconductoring standpoint, you're looking at least a week per mile. So again, more disruptions to customers to achieve that capacity increase.
Really impressive results on this one. And, I think the heat map's helpful to really understand the trends that exist seasonally. I think importantly, even on the low end of that spectrum, where in the summer when the ambient temperature is a lot hotter, you're seeing 18% gains. That's still really significant when you take into account the fact that, there's been studies done that even along the lines of a 5 to 10% increase in capacity is typically enough to essentially eliminate congestion on any given line. And so when you're talking about 18%, you're already likely eliminating congestion on that line altogether. And from there, it's just additional headroom depending on when you are, which season you're in the year. So lots of really useful capacity that you're able to get really year round.
Yeah, agreed. All right, so DLR, I mentioned DLR is not just for capacity gains. And here we'll look at how can DLR ensure that we are safely and reliably operating our transmission system. So just, I know the graph that might be a little rough to see, but just to explain those real quick, you can see DLR on the graph on the right is the blue line. Ambient adjusted ratings is the brown, and then you have static rating is the straight line. So this across the graph, that's a single amp rating for the line, and then the red line is the actual loading on the transmission line. So these graphs were captured during what at least the weather forecasters were calling a heat dome in the Midwest, right? So a big high pressure system that moved over Midwest in June or so of last year. And so we were seeing 90 plus degree temperatures and very little wind speed. So not a great time if you're a transmission line trying to feed air conditioning power and everything to your customers while sweating in the humid heat out there. So how did the lines perform and what did DLR tell us? You can see that the blue line here in both graphs actually dips below both ambient adjusted rating and static rating. And in fact, there's times when ambient adjusted ratings are telling us we have more capacity on the line, but DLR is telling us we have less. And why is that? It's because DLR is a much better method of rating your line. You're taking into account real-time wind speeds for multiple sections of your line. You're not making assumptions based on a single ambient temperature. You have multiple sensors along the line that are monitoring real-time conditions. And so this is a case where operators were able to look at this data at this time of stress on our transmission system and have confidence that, as you can see, the red line doesn't approach any of the rating systems. So we had the capacity we needed, but this is a tool that operators could use to feel comfortable operating the lines and ensure their safe, reliable operation.
Yeah, a couple of comments on this one, AJ. First, just AAR might be a term that some folks might not be
Mm,
familiar with, and we
yeah.
didn't define earlier. So just for folks who might not be familiar, AAR stands for Ambient Adjusted Rating. And you can kind of think of that as the stepping stone between the traditional static rating and the dynamic line rating. The AAR uses variable ambient temperature, and so you get a little bit of that more real-time information about the ambient conditions, but it does not take into account wind speed. And it turns out that wind is actually the biggest contributor to determining what the true capacity of the line is. And so that's where you get that sort of the brown line in the chart that's showing, as AJ talked about, some increases in capacity, even as once you factor in the wind, you might actually be seeing the opposite. And which brings me to my second point, which is, one of the things I love about this graph is it really illustrates an important aspect of DLR that I think sometimes goes underappreciated, which is when we think about DLR, the conversation's usually around how much added capacity can you gain. And of course, that's the primary reason we do this, and is super important. But there tends to be a little bit of a mental model that we have that because static ratings are conservative, and we're talking about increasing the capacity on the line, is there a trade-off with safety? It's like you can kind of think of, well, I can get benefit or I can get more safety, but they're sort of in tension with one another. And what I think is so important about understanding this graph is that that's not the case at all. When you're implementing dynamic line rating, you're implementing a system that gives you maximum capacity and maximum safety, because in those instances where the wind is actually dropping and the true capacity on the line is dropping, you're getting that information too. And so in that situation where you're experiencing the heat dome, you want to know exactly how much true capacity you have so that you don't run the risk of overstating capacity and introducing risk into the system. So I just think that's a really good example of illustrating that.
Yeah, good point. I mean, I think when you go to someone in transmission operations at our utilities and say, "Hey, we're going to run more amps across your lines," like their first reaction is, "Well, hold on, that's us taking more risk." And actually, your risk goes down. It's because all the points you just made, because we now know the true capacity of the line, both when it has more and when it has less.
Exactly right. So before we get into this one, this is another really cool example that we got out of this project. And just to kind of orient these last couple of slides, we're really kind of stepping through different ways in which we're able to get really meaningful value from the dynamic line rating data. There's the obvious way in which getting more capacity, reducing congestion, meeting load growth demands. There's the one we just talked about around safety and reliability. And then we're talking, this one is really a third kind of value stream that you might get by implementing technology like this, which is taking more of a intelligent approach to where you invest capital dollars. And we were able to use the DLR data to understand where a specific part of a line could be reconductored in order to unlock a lot of additional capacity. So AJ, would love to hear from you on how you guys did that.
Yeah, this was a very something we didn't expect to find with our DLR deployment, but thinking about the insights and how this technology can be used across the organization, it was an important one, and I think where we'll leverage this similar use case in the future. So in front of you is a 69 kV line in Ohio. You can see on the left, man, we're running through a lot of trees. Well, what does that really do? You can see kind of in the middle, there's a bunch of numbers with some red in the middle. That's the computational fluid dynamics model coefficients. So basically, what are the wind speeds in that area? They're bad. The trees block the wind. And so our static line rating assumption for this line is 2 meters per second for wind speed. That doesn't hold here in this highly vegetated corridor. And so we actually have lower capacity than we thought we did in this area. And this is a critical line for AES. It was selected because it's a generation outlet for for our kind of northwest service territory. And so how do we increase capacity on that line? Well, a standard approach would just be reconductor the whole line, because that's the way we would achieve greater capacity, and that would take roughly $1.63 million and at least 2 years in a 5-week outage. However, because you can see again on the middle graph here of the wind speed coefficients, we really only have a small section. It's actually just a half mile that you can kind of see on the bottom right here in that red line. That's the only part that's a problem. So we can actually plan to only reconductor that half mile, or if there's option to manage the vegetation and monitor results. We're looking at both options here. But do it for much cheaper. Do it for $400,000 and achieve this project in a year with only, let's say, a week-long outage, right? So this insight wouldn't have been available without DLR, and so it allows us to target our capital and deploy it efficiently to serve our customers.
And then importantly, once you've kind of addressed that one limiting section, you unlock the benefit of the DLR across the entire line, right? Because, we were
Yes.
something like a 10% gain in capacity overall, except for this section, which was driving it to be actually a negative gain. And so you sort of have a win-win of being able to get the proper capacity even with your existing rating, but then go even higher by unlocking the DLR capacity on the rest of the line.
Yeah. No, this is really a great use case, and I could see there's similar. We have other lines that we didn't talk about here, but it's similar to those. We have certain sections that are limiting your worst section of your line could be your limiting element. What can I do to just target investment in that area so that I can unlock the full capacity of the line from end to end?
Yeah, and it really kind of ties back to what I was talking about at the beginning of just sort of monitoring these assets and turning them more into intelligent assets. Because historically, if there was an issue with a line like this, you're basically, you're reconductoring that entire thing. And so by being able to target capital in a much more efficient way, you can use that capital for other pressing projects and start to allocate capital in a much more efficient way. So I thought that was really cool example. And then just to kind of tie that out, that was kind of the deep dive on the AES project and looking forward to answering some questions. Just wanted to close on this note. This is a technology that LineVision's been proud to deploy, not only with AES in Indiana and Ohio, but with a number of different utilities around the United States and even around the world. We're deployed in the UK, in Europe, Japan, and other parts of the world. And maybe even perhaps more importantly than just the geographic footprint is really the kind of maturity of or evolution of the adoption of the technology in the marketplace right now. When we were doing this a few years ago, we were largely doing pilot projects and kind of testing out the technology. Utilities were rightly asking good questions about the efficacy of it and really trying to make sure that it works. And increasingly now we're seeing partners like AES and many others who are thinking about how do we deploy this at greater scale and operationalize it, integrate it into our control room, and really start using it to solve some of those really pressing challenges that we talked about at the beginning. And so I'm really excited to see what's ahead as we start to see dynamic line rating and transmission line monitoring technology become a more critical part of how we operate the grid here and around the world. So with that, AJ, I really wanted to thank you for taking the time today, and not only for today's webinar, but for the great partnership over the last couple of years. It's been an absolute pleasure working with you and looking forward to many years of continued collaboration. And
Likewise.
with that, yeah, appreciate it. And with that, we'll pull up some questions and see what questions folks have. So first is a question for you, AJ. Which estimated potential capacity increase or value on the line was the minimum for you to decide installing sensors? So was there sort of a minimum potential gain from our profiling studies that kind of gave you the green light on whether to move forward with the line or not?
Yeah, no, great question. again, after in that line selection process, after we received the line profiling studies, you had to say, this is the potential of what DLR could bring. We also compared that to, okay, well, what is the available headroom from our current limiting element, which we limited our selection to lines that were conductor limited. So there were no other limiting elements in the substation or on the or elsewhere in the circuit that limited the rating. And then what's the next limiting element? So like, let's say the next limiting element is the conductor in the substation, and there's 12 MVA to get between your conductor and the substation conductor. So we looked at like that headroom and then what percent of that headroom would be meaningful to capture. Even a 10% increase in an area where we have a very critical line, for instance, I mentioned lines that run from our generation facilities to out to the grid. There's very limited, sometimes limited connectivity there. And so even a 10% increase can be meaningful for us. So I think it really is dependent, but I would say, yeah, in that 10% threshold was kind of our selection criteria.
Awesome. We have a question on what factors were considered when selecting lines, and I think we did cover that in the slides, but sort of part B of that question was congestion costs in particular. Was that one of the factors you all considered when selecting your lines? And if so, how are those costs measured?
No, great question. So congestion cost wasn't actually a major consideration for the deployment at AES. We looked at more customer-facing use cases. Congestion in PJM, so the regional transmission organization where our Ohio territory operates, is measured, and PJM does publish like its most congested lines. And I know other collaborators with LineVision, such as PPL or others, right, have looked at reducing congestion. AES, it was more on the reliability and customer, like integrating new utility customer use cases. And then in Indiana, congestion isn't measured by the regional transmission operator there, MISO, but it is important in which lines are limiting generation, the cheapest generation for flowing to customers. And so I think it is a factor to consider, but it depends on, again, the utility and the region where it operates on that use case. I don't know, Karthik, if you have any comments on congestion.
Yeah, and I think that's spot on, and it's a good example of one of the things that we do, we LineVision, when we're working with a new potential utility partner, we're really starting with what is the problem that we're trying to solve, right? Because to kind of to the point you're making, the challenges of, let's say, load growth or meeting new load that's coming into your service territory may or may not always be related to congestion, in the sense that it might be more forward-looking. Congestion is almost by definition sort of backward-looking, and it's like which lines have already experienced congestion. But if you're seeing more new load growth potentially coming into your territory, you might not be experiencing that congestion yet, but you know that you're going to need the capacity to meet that load growth. And so it's really more about kind of aligning around where the needs are and where they're going to be, and deploying the technology in a thoughtful way based off of that. Another one for you, AJ, are the DLR improvements over annual static ratings or seasonal static ratings?
So in Indiana, we use annual static ratings. And so the 3485 kV line that we presented, the average of 43% increase was over annual static ratings. In Ohio, we have seasonal static ratings that I think they adjust on like March 31st and October 1st. And so the gains are over the seasonal static. And both utilities are looking at how do we implement ambient adjusted ratings due to FERC Order 881. And so this study with LineVision, this deployment has allowed us to be more thoughtful about how we deploy AAR. As you saw on the slide where ambient adjusted ratings can sometimes overstate your capacity, we want to be very careful on how we rate our lines for ambient adjusted ratings.
That's great. I can maybe take this next one. How did the AES and LineVision team determine where sensors were necessary to implement DLR? So LineVision has a process that we go through to scope out each of our projects. And it's a combination of running computational fluid dynamics to understand where the potentially limiting sections are. We also take into consideration, a lot of different factors that would potentially drive where a potentially limiting span could be. And so those are things like historical weather data, changes in line heading, changes in elevation and vegetation. Really, we're looking for things that could impact the flow of wind through the conductor corridor. And we want to make sure that we're placing a sensor such that we're capturing all of those sections that could at any given time be the most limiting span, since again, it's the most limiting span that's going to drive the overall line rating at any given time. Importantly, we don't need to place a sensor at every tower. We're typically placing a sensor one every 2 to 3 miles. But again, that depends on the specific topography that we might find. There's another second part of that question. Did AES and LineVision team consider using sensorless DLR? And if so, why didn't the team pursue sensorless DLR? And AJ, I'll hand that to you if you want to take a crack at that one.
Yeah, going back to the discussion about what level of risk do you want to take on as a transmission operator, right? You're responsible for operating the backbone of the electricity grid for your customers. But we did not feel comfortable, and I think there'd be a lot of utilities that would echo this, of using sensorless DLR. I mean, you saw in the example where the sensor was limited by trees. Yes, there are technologies that can go out and say, well, we assume this vegetation might hinder the wind speed here, and we'll, but all the key word there was assume, and having a sensor in the field reduces that assumption. When you have sensorless DLR, it's hard to say that you're not taking on more risk in operating your system to a higher capacity because you are making assumptions. And so our operations team, it was a non-starter to not put a sensor on the system that we could rely upon. And to Karthik's earlier point, like, yes, we have a sensor every mile, but sometimes we even have two right next to each other. Why? Because the line heading changes. And we can see drastically different wind speeds based on, the line is at a 45 degree angle. And so we put a sensor on either side. Those sensors can see different wind speeds, which really affects the line. So I don't see the ability to do a sensorless deployment, at least with AES.
Great. What maximum operating temperature was used before and after the DLR install? That's an interesting question, right? So I think this may be an important concept. The maximum operating temperature does not change, right? So the MOT of the line is what it is based on the actual, physical properties of that conductor. What we're doing is saying, how much additional current can you run until you hit that MOT, right? And so that's kind of the nuanced difference between the temperature itself, what is that maximum, but also understanding what are the real world conditions that allow you to run up to that MOT, and you'll typically find that the dynamic line rating is higher than the static rating for that given MOT. And there's also a question of what percentage of time was the DLR real-time rating below the prior static rating on the 345 kV line. I think we had that in the slide earlier, but I think it was somewhere so around 10% of the time, I think it was, AJ, because 85 to 90% of the time we saw DLR was greater than static. Does that sound right?
Yeah. So what percent of the time the 345 kV line was above static? What percent of the time?
Was the DLR below the static rating?
3% from the 1 year of data. I pulled up the data you sent me for 1 year, the granular results as we've been talking. And so, yeah, 3% of the time for the 345 kV line, we saw dynamic line ratings less than our static rating. So, and that was primarily in the summer months. Actually, only in the summer months, if I'm looking at, yes.
And that, for what it's worth, is very representative. That sort of 97% of the time plus of DLR being above static is pretty commonly what we see across our projects. Um, let's see. How would the utility make decisions on load on their lines if the capacity gains with DLR vary quite a lot between summer and winter? How does this play into planning? That's could be a tricky one. You want to take a crack at that one?
Yeah, that's the $1 million question. So
Yeah.
I'll just say DLR, the capacity of DLR has not, at least to my knowledge, been used in the planning case. So um, in the US, at least. Karthik, refute me if I'm wrong, right? We are right now deploying DLR in operations, but ultimately the insights we're getting into how our lines perform and what the true ratings are can you can think about increasing the the static rating of the line, right? Or increasing um, the base rating line, and that does give you capacity. If you look at the 345 kV line, for example, like only 3% of the time we are below static. Is there a solution, whether it's switching, whether it's deploying energy storage, or other um, load flexibility that we could couple DLR with um, that another solution to guarantee a capacity that could be used in planning. So AS is looking into that tool because we need creative solutions like that in order to um, avoid building out the grid for the demand we're seeing.
That's great. Do you assume a fixed wind speed in calculating your AAR? I'll answer that one. The answer is yes. That's almost by definition. You're assuming a fixed wind speed and only changing temperature for an AAR. How long did AES and LineVision take to determine which lines should receive DLR installations? Um, from the time that AES decided to pursue DLR generally, how much time did it take for AES and LineVision to identify which lines should get DLR?
We met in April, Karthik,
Hmm.
late April, and were we selected the lines by May, June timeframe. So let's say 2 months to kind of initial conversation to selecting lines. And then just based on construction schedules and things, we deployed in September of 2023. So there was some lag time there, but that was mainly due to just just fitting in with the kind of the summer run work. But the installation was the I like to say there's nothing done faster in transmission than hanging a DLR sensor. Our transmission line crew was in and out 30 minutes per sensor, roughly, not counting travel time, obviously, between sensors, but it's a very quick process.
Great. Um, what do you see as the major barrier to installing DLR, and why aren't more utilities deploying the technology? I can take a crack at that
Yeah.
one. I think that's uh, a really important question, and a lot of it, I think, really comes down to utilities are rightly um, risk averse when it comes to deploying new things. They have very important jobs running critical grid infrastructure. And so sometimes there's the mindset of, we want to see others doing it, which is candidly partly why we do webinars like this, right? We want to share the results that we are seeing from utilities that are doing and showing that it is a proven technology and that it works really well. The good news is that we're starting to see that adoption accelerate, right? I think now that we've had a number of examples where utilities are using it successfully, you're starting to see that acceleration of adoption. I think the FERC 881 order that's sort of driving the utility space in general to move into more of that hourly rating is also going to lower that barrier to adoption because a lot of the sort of processes and systems around it are virtually identical. Because once the for example, EMS is in place and able to ingest hourly rating data, replacing that AR with a DLR becomes relatively trivial. So we're excited to see kind of where things go from here as things start to move even faster. Um, AJ, I don't know if you've got a number you could offer off the top of your head on this question, but it says, what percentage of otherwise good candidate lines were limited by something other than the conductor? So let's say a next limit
Mm,
element kind of made it not a great near-term candidate for DLR.
Yeah, maybe of the 15 that we just kind of came up with without looking at our, I think it's FAC 008 or facilities ratings methodology information. Uh, maybe 5 fell off just because the line wasn't the limiting conductor. There might have been even as something as small as a relay. So a substation relay has a current rating they can handle on the secondary from the current transformer that takes the readings. And so it might have been a minor project, let's say $250,000 and 2 or 3 day outage at the most to switch out the relay. But we didn't even want to have that headache of dealing with being dependent on another project being complete. So I would just say, yeah, maybe a third we ruled out because of higher being limited by other elements. But some of those were minor and could have been fixed in the capital plan.
Yeah. And while we didn't pursue that in this particular project, LineVision has certainly seen that in other projects where by instrumenting a line with DLR, it actually helps to make the business case for doing the upgrade for that next limiting element, right? So if you can actually show using data that if we just invest a relatively small amount of capital to AJ's example, like to change that relay, the capacity we're going to get is an extra, 30, 40% because that's what we know we're going to get from DLR. And so all of a sudden it makes a lot more sense to make that upgrade to the next limiting element to increase the capacity of the overall facility. So that's another way, another sort of example of using that more data-driven decision making. So I think that is all the questions that we saw. And yeah, I think we're good to wrap this up. AJ, anything else that you wanted to share before we sign off?
No, I just maybe comment on what's next for AES with
Yeah,
DLR
please.
and LineVision. So Karthik, you mentioned how do integrating the data into our energy management system or EMS and coupling that with SCADA data. So that's on roadmap for us. We're actually in process of upgrading our energy management systems for FERC 881. And so, looking that once those systems are upgraded, they enable third-party ratings information to be essentially plugged in. And so we're going through that integration process now. I might have saw a question about that. And then we're seeing these requests from customers. We're seeing large 1 gigawatt, 2 gigawatt data centers siting especially in Ohio service territory. You remember it's a lot more land that we cover. It's a lot more options for data center and industrial load growth. So we're seeing those customers now. And in those discussions, we're evaluating tools such as DLR in delivering more clean energy to customers because there's clean energy attributes that can be the cleaner electrons can flow with increased capacity on lines. We're looking at how do we use dynamic line rating to mitigate construction outages. So I mentioned outages a lot on this call, right? We need to build this transmission, the firm transmission to serve these customers. In the meantime, there's going to be lines that are temporarily affected and might need to carry more power. And usually outages are in those periods. If you remember the graph with the kind of the heat map, are in those kind of shoulder months. We don't take outages in the summer as a utility, right? Or in the dead of winter. And so DLR is well posed to deliver more capacity when we need it during construction outage. So anyway, we're looking at all of those solutions to serve our customers. So again, excited about what Karthik we're gonna hopefully continue to keep working on in the future together, and maybe we'll have another webinar about serving customers creatively as our next act.
Absolutely. Looking forward to it. Thanks so much, AJ, and thank you all for attending today. Really appreciate the attendance and the great questions that you all submitted. Looking forward to the next one of these, and encourage you folks to reach out to each of us. We've got our contact information here up on the screen. feel free to reach out to either AJ or myself if there's anything else you want to discuss or any questions that we didn't get to. So with that, we'll sign off. Thanks, everyone.
Thanks. See ya.